webinar. Just a couple quick announcements. First of all, this week we have a presentation. Next week is the SWAT meeting, and so we're going to skip for next week. And the following week will be, we have a webinar scheduled, and that'll be the 5th of July, so right after the 4th of July weekend in the US. So today we're fortunate to have Alex Wineteer, who's going to talk about Odysea mission, measurement simulator, and particle dispersion. And I'll let you take it away, Alex.
Okay. So I have a kind of a range of topics to talk about today. Of course, starting with the mission itself, and then going into some of the measurement simulator that we've been developing for Odysea. And finally, I'm going to talk a little bit about a particle dispersion study that I did a little while back and that we're going to publish eventually, but it's very related to Odysea. And of course, I want to acknowledge Ernesto and Hector, who have contributed a lot to this work in one way or another. Let's see if I can, there we go. Okay, so I think probably all of you know what Doppler scatterometry is if you're here today. But of course, we have a wide swath that's formed using a spinning pencil beam radar, and we're able to measure simultaneously the measurements of ocean vector winds and currents. So the wind measurements are based on heritage scatterometry. Think of something like QuickScat, but we operate at Ka band and can get a higher resolution measurement. And then the measurements of currents are done based on the Doppler shift of Bragg waves at the ocean surface. So this measurement's been proven from an airborne platform. We have an airborne mission called DopplerScat that is doing this today. And this measurement can be scaled to space given sufficient power and antenna design as the primary two constraints. So that's exactly what we're trying to do right now. We're proposing a mission called Odysea, of course, led by Sarah. And the sort of primary mission design for this is a 4-day exact repeat cycle. We have a 6 a.m., 6 p.m. sun synchronous orbit at around 630 kilometers with a instance angle of 59 degrees. That gives us about a 1600 kilometer usable swath. The actual swath is larger than this, but we blank portions of it. We get about 90% ocean coverage in a day with spatial sampling of about 5 kilometers, and we're aiming for data latency of about 6 hours. So there are a few main surface current error sources. The first one is random instrument noise and sub-footprint scale variability. We have noise from pointing errors and then systematic GMF errors. And so this plot on the right is showing primarily this first bullet, showing the instrument measurement noise and sub-footprint scale variability. So the main takeaways here are that for surface currents, the edges of the swath have the highest errors, and then the wind speed has a pretty big influence on the total surface current error. So lower wind speeds like this blue line, you end up with a higher error than higher wind speeds like the red line. So what we've done in the measurement simulator, at least the simplified version of the measurement simulator, we've taken and put in a 35 centimeter per second baseline random measurement noise, 10 centimeter per second random pointing error, and blanked the center and edges of the swath where the measurement errors exceed what we think is acceptable, which is typically 50 centimeter per second. For the wind side of things, again, this is really similar to traditional pencil beam scatterometers. The random measurement noise is primarily due to instrument signal to noise ratio and viewing geometries. But there are systematic GMF errors that we need to think about. So if you've ever seen a plot like this from scatterometers with wind speed error versus cross-track location, you end up with something that has higher errors in the center, higher errors on the edges, and you have what we call a sweet spot near the center, between the center and the edges of the swath. So if you kind of simplify this into a simple error model, which is what we've done for the simulator or the simplified simulator, we get a speed of the greater of 10% or 1 meter per second error in speed, and then a direction error of 20 degrees for 3 to 10 meter per second wind, and 15 degrees for 10 to 20 meter per second wind. And these are kind of similar to traditional scatterometry, but we're doing a little bit better than I think QuickScat did at wind speed, and we're going to be doing it at higher resolution, as I'll show in a little bit. So this simulator that I've been mentioning so far, we actually have two simulators. One is a more complicated simulator that does all of the radar, SNR, and look vectors and everything. That's not the one I'm talking about today. This one is a more simplified simulator that we're planning to release to the public as an open source release. It's based on Python. Right now it's in a Jupyter notebook, but I'm planning to port it into more of a standard Python package you can import. The orbit is this pre-simulated 4-day exact repeat orbit that I was talking about on one of the first slides. The error model is implemented for a baseline, a goal, and threshold mission, and these can be set by the user as you like. The baseline mission is the one that I've mentioned so far. Code is available for co-locating ocean atmosphere models, but likely it will have to be minorly adapted to whatever your model is. Right now it's using a coupled ocean atmosphere model from the MIT GCM. JPL is, like I said, we're working towards a public open source release. So hopefully in the next few months, we'll have it fully released. Okay, so this is some of the results from the simulator. This has no noise in it yet. This is just showing the global coverage that Odysea can achieve. So in one day, you can see this top pane for surface currents and winds. We get pretty much near global coverage. It's really just near the equator where we have some missing diamonds between the ascending and descending passes. At 2 days, we're pretty much fully covered. We have these little tiny diamonds that will very quickly fill in. Okay, so this is a global sampling pattern. So I know there's a lot here. So just starting on this left-hand side, this is a global map, latitude and longitude of the mean time difference between samples. So if you take a bunch of Odysea passes and look at the mean time difference at the equator, it's about daily sampling, 24 hours. Every 24 hours, you get a sample. And then as you move towards the poles, we get more like every 5 hours sampling. And then if you look at the minimum time difference at the equators, it's less than 5 hours at the poles, it's less than 5 hours. And then at the equator, we can get about 12-hourly sampling at a minimum. So that just means that as passes come along, there will be different minimum sampling times between different passes. If you integrate this across longitude, you get this plot on the top for mean sampling time differences. Again, this shows pretty much the same thing. You get about 24 hours at the equator and significantly less, around 5 hours at the poles. In 4 days, this plot on the right, and I'm mentioning this because we have this 4-day repeat cycle. In 4 days, you get about 30 samples at the poles and about 5 samples at the equator. Now, this is starting to put noise into the picture. So this is surface current U component, surface current V component, with noise on the top and without noise, without noise on the top, with noise on the bottom. And there's not a lot to see here because you can't really tell that there's noise at this level. So I'm pretty much just going to skip this and go to the next slide where I've zoomed in a little bit. Okay, So this is showing a picture of the Gulf Stream. This is with 4 days of simulated Odysea data using a 2-kilometer coupled COAMPS model. There's 11 passes over the Gulf Stream in those 4 days. All those passes are shown here with noise from the simplified simulator. And you can see on the left here is the 4-day average model, and on the right here is the 4-day average Odysea. So comparing these two, you get an RMS error of about 10 centimeters per second. So we're doing pretty good in a repeat cycle, I guess, looking at the repeat cycles. For individual passes, the errors are going to be what the baseline error was in the simulator, which is about 35 centimeters per second on the speed and 25 centimeters per second on the components. If we look at relative vorticity in the same region, on the left is model for a 4-day average. In the center is Odysea for a 4-day average. And on the right is Odysea in a single swath, so no averaging at all here. And you can see a couple of things here. So of course, for the average data, we get a lower noise level than we have in the single swath data. However, if we look at the standard deviation signal to noise ratio, we get about a factor of 1.7 on the SNR for 10-kilometer smoothing in Odysea data, and a factor of 2.7 in 15-kilometer smoothing in Odysea data. And this is really largely due to the strong vorticity in this region. The Gulf Stream has really strong vorticity, and so we're able to measure it very, very well in single swath data. If we look at something more globally, these are the results from the simulator for in-swath resolution speed on the left and the 4-day repeat cycle on the right. So starting from the in-swath resolution, this is based on getting a standard deviation signal to noise ratio of 3. So that's a variance SNR or a spectral resolution of 10. So you can see for regions where you have strong currents, places like the Gulf Stream, a lot of the Southern Ocean, you get a fairly high speed resolution, even just in swath. For those regions, we're really resolving the grid scale of 5 kilometers. And since this is a wavelength resolution, 10 kilometers means we're resolving this grid scale at 5 kilometers. In places where we have weaker currents, we're getting resolutions that are more like 70 kilometers, depending on where we are in swath. However, for a 4-day repeat cycle, we can do much, much better. We can really resolve the grid scale down to 10-kilometer resolution for almost the entire globe. Looking at these same plots for curl and divergence, these are both for the 4-day repeat cycle. You can see in areas, again, where you have really strong curl, you can get really, really great resolution. You can get this 10-kilometer wavelength resolving resolution in the Gulf Stream. But places where you have weaker curl in the ocean, we're getting lower resolution. We're getting something like 40 kilometers in those regions for curl. Then looking at divergence, we're getting somewhere in the range of 30 kilometers for most of the world's oceans in this 4-day repeat cycle. Okay, so looking a little bit at the winds that Wacom or that Odysea can measure. On the left here, we have the model for a single Wacom swath at 5 kilometers. And on the right, we have a single Odysea swath at 5 kilometers with noise. On the lower left is surface current relative vorticity at 10 kilometers for Odysea. And then on the right is wind relative vorticity, again, measured from Odysea. And you can see a lot of really interesting stuff here, especially in terms of the coupling that we'd expect between the surface current vorticity on the left and the wind relative vorticity on the right. So we expect to see a negative coupling, and we do indeed see that if we look at the slope of that coupling just in this instantaneous measurement swath. We can actually measure the coupling between those two, comparing the truth with no noise and the Odysea measurement with noise. And as you can see, as you increase the smoothing, these two estimates of the wind current curl slope begin to really begin to converge, and we get a measurement that really closely matches the true coupling at about 20 kilometers. So in the Gulf Stream, we can start to look at these wind current couplings at 20 kilometer resolution or so in curl. And that's probably an order of magnitude improvement over what we've been able to do in the past compared to using geostrophic currents and traditional scatterometry. Okay, so that was part one, just looking at some of the resolution that we can get and the simulator results that we can get for Odysea. We can get around 1 sample per day near the equator, up to 5 samples per day near the poles. The speed resolution of 10 kilometer resolves the grid scale in 4-day maps. And then if you look at instantaneous in swath speed resolution, we're looking at between 10 and 80 kilometers, depending on the local current strength. The vorticity resolution is between 10 and 50 kilometers for the 4-day maps. And in regions of very strong vorticity, we can actually resolve around 10 kilometers in swath instantaneously. The divergence resolution is about 20 to 50 kilometers for the global oceans in 4-day maps. And I need to look at the in swath divergence resolution. I didn't get around to that for this presentation. The combination of equivalent neutral winds and currents allows Odysea to measure the coupling coefficient between wind and current curl instantaneously in the Gulf Stream at about 20 kilometers resolution. Now, that's not to say we can't do better than that. We can actually use lots of measurements, lots of passes over the Gulf Stream to get at that resolution, or to get at that coupling at a higher resolution. Okay, so the second part of this presentation, I wanted to go through some particle transport work that I've done in the past, looking at some of the different processes that go into controlling particle transport, and then also looking at how we might be able to measure or estimate particle transport based on spaceborne Doppler scatterometry or Odysea measurements. So in general, a variety of, or really the range of oceanographic processes control surface particle transport. And as to say that resolution and physics both matter. So this is a plot taken from a paper by Victor Onink that looks at the transport of microplastics in the world's oceans and tries to separate between different types of currents. And so he's done this looking at Ekman currents here on the top right, geostrophic currents on the bottom left, Stokes drift on the bottom right. And if you advect microplastics just using these 3 types of currents, you get these patches that form that don't really quite look like what we really see in the world's oceans for garbage collection. But then if you add all of these currents together and do the advection, you get a picture of microplastic advection that really looks more like the garbage patches that end up forming in the oceans. So the point of this paper really was to show that you have to think about all of the oceanographic processes that can advect particles if you want to see true particle advection in the oceans. So I've tried to do something similar, albeit on a smaller scale in the Gulf of Mexico, where I've used this package called Ocean Parcels to horizontally advect particles at the surface of the ocean in the Gulf of Mexico. We've released about 10,000 particles at the Deepwater Horizon platform, where there was the oil spill years ago. There was One particle released every 6 seconds thereafter, and the simulation ran for about 5 months total. So I've also separated by different current types to try and get at what we can do based on the current state of the art using, Odysea style geostrophic currents, Ekman and Stokes drift estimated from winds or scatterometry, and compared that to a full model control run and runs based on something like what Odysea could do. So I've actually split up the geostrophic components into 2 sets that I'll show here. One is an Odysea style that I'll call sort of a lower resolution run. Then I've also used a higher resolution geostrophic current for advection that's kind of like a SWOT resolution. I'll show that more on the next few slides. Okay, so these are some of the results just in physical space for particle transport. Looking at the top pane, this is the model run. So this is really a control run where we've taken model currents from the 1/48th degree MIT GCM model and advected particles using those currents from the full resolution 1 hourly model. And then we've also added a Stokes drift onto that. So you can see we have really a lot of advection in just 4 days towards the center pane, and then T0 plus 9 days in the far right pane. Particles start out from this red dot at the Deepwater Horizon platform and start moving out into the middle of the Gulf of Mexico, being pulled into the large scale geostrophic flow. However, it's, and I'll show this more on the next slide, it's really a lot of the smaller scale geostrophic flow that starts out this advection and gets particles moving to where they can become entrained into this larger scale eddy in the center of the Gulf of Mexico. So if we look at something more like what Wacom can do in the center pane, so this is currents that have been sampled as if Wacom saw them at the resolution that Odysea, I'm used to Wacom, the resolution that Odysea can see, and with the time sampling that Odysea would have, we see something fairly similar to the model results. It's not exactly the same, of course, but we're starting to get this transport of the particles in black sort of out towards this center eddy and being advected all over into the Gulf of Mexico in just a few days. However, if we do a summed experiment where we take geostrophic currents at a resolution of about 14 days and 132 kilometers. So I've smoothed SSHA at 14 days and 132 kilometers, and then computed geostrophic currents from that, added on Ekman currents, and then added on Stokes drift. We get these results. So you can see in this case, the particles really don't make it very far. They pretty much sit in this region near the coast, right near the Deepwater Horizon platform, and never really make it out into the Gulf, at least not for these 9 days. I'll show that they actually make it farther out over the course of time. But if we're just thinking about short timescales, we really need this higher resolution that we get from the model and from Odysea if we're going to more accurately represent where particles get advected. So these plots are showing a displacement PDF, which is looking at the displacement of particles just starting from this red dot. How far is a particle from that red dot at a certain time? So the x-axis in a single plot is time in days, so 0, 50, 100 days. And each of these plots is a different experiment. The y-axis shows the displacement, or the displacement PDF, and the PDF is the colors on the right. So just starting with this wind, starting from the model plus Stokes drift. So this is kind of our control experiment. We can see that as time moves along, particles get advected. There are more particles farther away from the starting point. The total displacement PDF grows, And if we move over to the Wacom case, we can see that we get something kind of similar. There's a little bit of difference at these starting time scales. So, at very small time steps, there's a bit of difference, but not really too much. There's not a lot to see between these two cases here. But then if we move over to a couple of the other cases, so these three experiments on the top right are the summed cases of geostrophic, Ekman, and Stokes drift for different resolutions of geostrophic currents. If you use very, very high resolution geostrophic currents, far greater than what we can resolve with the VISO or even with SWAT, we get particle advection that looks kind of qualitatively similar to the model case for larger timescales when you go beyond 50 days. But if you start moving towards these smaller timescales, we're missing a lot of the particle advection. So a lot of the particles are at displacements smaller than what we'd expect based on the model, even these very high resolution geostrophic summed runs. If we go to something more like what we can do today, either the center right or the far right, with 14-day, 132-kilometer geostrophic currents, the advection takes a very long time before it really starts to pick up. And that's what we saw on the previous slide, with all those particles kind of just sitting at the oil platform. We see even at 100 days, we're missing a huge amount of displacement in the displacement PDF. And if we go to the even lower resolution geostrophic currents, the effect is even more pronounced. If we look at individual experiments, so this is just Ekman, just Stokes, only geostrophic at this smoothing and only geostrophic at the the lower resolution smoothings. You can see Ekman and Stokes drift have a small but important effect. If we look at just the very high resolution geostrophic currents, this has the highest effect of all. So from this, we can really start to say that the resolution is very, very important. The resolution of currents that we use is very important towards getting this this displacement PDF that we expect based on the model. And then as we smooth those geostrophic currents farther, we get even less displacement than we get in this higher resolution case. So the takeaway here is really that you can get very good displacement PDFs using Odysea compared to the model, or if you have very high resolution geostrophic currents. However, even at the small timescales, those geostrophic currents aren't quite enough. So this is a kind of a similar plot, but this is using relative dispersion, which is a measurement looking at the dispersion of particles relative to the center of mass of the particles. So this is a little bit more quantitative of a measurement than the previous slide I showed. So what this is showing are the same cases. Again, this summed experiment with geostrophic Ekman and Stokes at these three resolutions of geostrophic currents, and then model and Wacom, or Odysea now. So we could see that as we start to move along the time scale, x-axis is time, y-axis is relative dispersion, particles begin to disperse. And in the Wacom and model experiments, these lines really track very well for smallish time scales. So as we move through these small time scales, however, the summed experiments have not quite an order of magnitude, but a significant reduction in relative dispersion compared to the model case. Then as we move towards these larger time scales, as we start to get towards 10 days and out towards 50 days, like we were looking at earlier, we can see that the higher resolution summed experiment eventually actually catches up with the model and shows a similar relative dispersion compared to the model. But at these lower resolutions, we actually never quite catch up to the model results until maybe very far into the run. So the point is, if you're looking at timescales that might be relevant to things like search and rescue, to things like if you're trying to contain an oil spill, these smaller timescales are very, very important. And so having these high resolution currents from a mission like Odyssey could really help constrain where we expect particles to go. Looking at this bottom pane, this is just to show the kind of relative contribution of different components compared to the model. And you can see that at the shorter timescales, really all of the physics that we included, the Ekman, the geostrophic, and the Stokes drift, they all have important contributions that are similar in magnitude. But then as you start to move up into larger timescales, the geostrophic currents really take over, which is kind of what we would expect. Okay, so the part 2 summary here is that horizontal particle advection is driven by a large variety of oceanographic processes across the range of scales. We really need high resolution measurements and really good temporal sampling to reproduce ocean transport along the surface, especially at smaller timescales. There's an orders of magnitude underestimation in particle transport if we use state-of-the-art geostrophic currents. And higher resolution sea surface height anomaly from SWOT will help, but probably not fully reproduce the expected model transport. And then finally, advection using Odyssey surface currents can pretty closely match the model results. And so that's all I had today. I'm happy to take questions. Thanks.
Thank you. Maybe we can give you a round of applause and then start some questions.
Thanks.
Please, you can raise your hand or put questions in the chat. And maybe to start things off, I'll just ask you, you did this advection work for the Gulf of Mexico. Have you thought about whether there would be any changes if you looked elsewhere in the world?
I think there probably will be changes elsewhere. One of the main things that really drives the transport in the Gulf of Mexico, if I can go back here, it's really this loop current eddy. Once things start getting entrained into that loop current, they start shooting out along the Gulf Stream and really get advected strongly. So I do think there will be differences depending on where you are in the world, depending on the physics. That'll strongly influence the relative contributions of geostrophic and Ekman and Stokes of all of the physics involved. Yeah.
I also know the wind and wave climatology is sort of unusual in the Gulf of Mexico.
Yeah.
Because it's a pretty enclosed basin. It doesn't get a lot of, there's not a lot of swell coming in from outside. So
right.
The winds are really, or the waves are really locally driven.
Yeah, one of the things I noticed when I have videos of this actually, you can actually see when storms come through and they start pushing particles with Ekman and Stokes. So they start, because there's no windage, it's all Ekman and Stokes. Starts pushing particles, kind of out from this trap that they're in the region of the oil platform, and starts pushing them around and gets them entrained into the larger geostrophic currents.
How hard would it be to do this elsewhere?
Not that hard, just takes time.
Yeah. Okay, I see Dudley has his hand up. Want to go ahead, Dudley?
Yeah. Hi, thanks, Alex, for a great presentation. I'm particularly fascinated by this particle advection analysis that you did, because I think if you can get the search and rescue people interested in this, it won't hurt at all in terms of, motivating this mission. Nice to get that audience involved. I want to go back early on and then throughout your talk, just ask you what I think is a simple question. You talk about resolution a lot, and I may have missed it in the beginning, but could you define exactly what you mean by that? Are you talking wavelength resolution, diameter of features, radius of features? What do you have in mind?
So it's really wavelength resolution, and you know, it's almost identical to what you've done in your paper. So it's just the standard deviation signal to noise ratio, smoothing using the wavelength of the, I think we used a Gaussian filter, but similar to your Parson filter approach.
Well, those are some pretty impressive resolutions that you quoted then. I was thinking that you must be talking about radius.
Well, it's a little bit different from what you got in your paper, because if we look at some of these things, like your paper really looks at the you know, the California current, where you know, some of the currents are a little bit weaker. It is harder to get the high resolution that we wanted over there. But then if you move towards these very strong currents in the Gulf Stream, you start to get the much higher resolution.
Well, that's pretty exciting.
I think so.
Thank you for a great presentation.
Yeah, of course.
Looks like Clément is next.
Yeah, hi. Yeah, thank you very much for this presentation. And so I actually had a question really related to the resolution that they just asked. So we are on the right slide. I was wondering, when you talk about resolution that reach about 10 kilometers, but at 4-day repeat cycle, what does that mean? Because the time scales are very short. So what do you compare with the smooth field as well? Or do you compare with a snapshot, which wouldn't give the same result?
No, this is with the smooth field.
Okay. So yeah, so that doesn't mean a lot. Actually, I would guess for the case of the repeat cycle, because at 10 kilometers, the eddies move within 4 days. So you actually don't capture actually the right front, the precise fronts, for instance.
You're right. You're right. There will be some degradation due to the movement of you know, eddies, but it's really just a question of how, and I probably should have put this in the presentation, how I did the resolution calculation. But it's again very similar to Dudley's paper, where he looked at SWAT and Wacom resolutions, comparing the smooth model fields to the smoothed Odysea measurements.
Okay, yeah, thank you. Yeah, because the smoothed residual must be very, well, almost zero at 10 kilometer wavelength, I would guess.
I'd have to look. Yeah, you may be right.
There's a comment. Oh, go ahead.
Go ahead. I'm done. Yes.
There's a comment from Ad in the chat. Ad, do you want to unmute and bring this up?
Yeah, I think it's a minor point for your comparison, but of course the oil spill affects the sea surface, the wave generation, it changes albedo, so the physics will be different. But since you compare model world with a reduced model world by instrument, then it doesn't matter really, I think. But for practical purposes, I would say you have to be a bit cautious.
You have a good point. Yeah, for oil spills, it'll actually be difficult to get wind, and probably very difficult to get current measurements. So I'd kind of expect, you know, you'd have to measure the regions around the oil spill. Yeah, that's actually a really good point.
Yeah.
Oh, well, Melanie has her hand up, so let's go with that.
Oh, okay, thanks. Yes, Alex, thanks for a very nice talk. Kind of continuing on what Clément said about the features moving during the 4 days. One thing people have mentioned is the possibility that researchers would assimilate the in-swath data, you know, to make like reanalyses essentially, which would obviously be the ideal way to dynamically interpolate. Just wondering if you know if anyone is thinking about doing a simulation of that, like maybe using the MIT GCM as truth and then some other numerical model to try to assimilate the data into.
So I know there's been some interest in the past in doing that. primarily at NRL. We haven't actually, committed to doing it yet, though we haven't fully talked about doing it. But it's something we really should look at, because I think we can have a great impact on surface current models by assimilating these data.
And winds too, probably, if it was a coupled model. Yeah.
Yeah.
Thanks.
Roger?
Oh, hey, Alex. Yeah, nice talk. I was wondering just a couple of details about the particle transport simulations. Namely, what exactly do you mean by Ekman currents and by Stokes currents? How exactly do you compute those?
Yeah, so another thing that maybe I should have had in here. So Ekman currents I compute just based on simple Ekman dynamics. I just it's basically a percentage of the wind at 45 degrees to the wind. And then Stokes drift, I actually did it two ways. One of which was a wind parameterization, and the other of which was just taken from ERA5 for the same dates as this model run. They actually produced kind of similar results. So I just showed the wind parameterization for this one.
Okay, thanks. So that means you're using sort of the traditional classical Ekman layer model for the very surface currents.
That's right.
So that probably does underestimate the wind-driven transport right at the surface by a significant fraction. And it might be different actually in the model. I'm not sure what the vertical resolution of the model is near the surface. You might squeeze a little bit more out of the wind if you have a more realistic representation of that surface shear.
Okay, I could believe that. I mean, just looking at these results, certainly the Ekman and Stokes, it's a fairly small contribution. So yeah, that might be true.
Thanks.
Yeah, thanks for the suggestion.
Alex, I wanted to come back to the temporal resolution, the 4-day sampling question, and ask really, I guess I'm wondering in the model how much the current does evolve over 4 days. Clément alluded to this. So do we have an idea of what the decorrelation scale of the current would be and what the ideal sampling would be to capture that?
Well, I certainly don't have it off the top of my head, but maybe we could look at it.
Yeah.
And I'm sure it depends a lot on the region and the driving physics.
Yeah, it sort of drives at this overall question of representation error. What are we sampling? What's the scale that we need to measure at in order to capture the variability?
Yeah.
So, well, maybe something to look at down the road.
Yeah. Sorry, I don't have anything really insightful to say. It's you're right, though. It's something we should look at. Yeah.
Rick.
Hi, Alex. Nice talk. I'm kind of thinking a bit freely about the fact that the simulator might not have a dependence on the atmospheric state in the simulation of errors, right?
No, it doesn't.
So, like, what if it was possible to somehow couple the convergence, the curl divergence in the wind field to the generation of errors in the ocean current? I'm thinking very freely, so I don't know if you want to even answer that. It's just kind of
so it's certainly
yeah, go ahead.
Well, so what I was mentioning earlier, if I can get back here. So the really driving factors in the surface current error are this random measurement noise, and then if we design the instrument right, to a lesser extent, the pointing errors. So there's this dependence on wind in there due to the instrument signal to noise ratio, which is dependent on the wind speed. Lower winds, you get higher errors. So in some ways, what you're describing might kind of be in that, but I also think that it might end up being, you know, a little far down compared to the error model that we're producing right now. I don't know. It's an interesting thought, though. It's something to think about. Maybe once we get a little farther into the development, maybe we can start thinking about it.
Ernesto.
Yeah, if you could just follow on to Rick's question. I think that the main process that we need to catch that's not caught right now is rain and rain dropouts. And that will influence the computation of derivatives significantly. So that's something that is potentially, especially in the tropics, something that we need to take a look at. Luckily in the tropics, the tempo evolution is a lot slower, and maybe we can get away with it.
Thanks, Ernesto. Mark?
Alex, great presentation. For the conditions where the currents and winds would change the most, you typically have very strong winds, which are conditions where you're going to have more accurate signals based on this plot. And there are also conditions where our modeling efforts show that there's a stronger coupling between the wind and the current. So the signal we want to see is better as well. So if you could do some of these studies where we account for that, we might find that the features that vary can be resolved better, and the features that don't vary, where we have trouble, we can average over a longer time. So it looks like it's a pretty nice combination of capabilities versus the real variability, better than might be shown in this study. You're
absolutely right. What I used in the study is more like the 6 meters per second or so wind speed. And so really, like you say, if you go up to those higher wind speeds, we get really, really nice current velocity errors. And so, yeah, I'd absolutely expect to get better performance in those regions.
Nonetheless, it's already great performance, so that may be mute.
Well, no, I think it's a good point, though, and we should be transparent about the places where we can do really well and the places where we don't do as well.
Clément put a question in the chat about the simulator. Clément, do you want to just go ahead and ask that?
Well, yes. So, well, it was first a comment says it's really great to have it available. And so my question was, well, also that it might be useful to also release a already simulated data set, like I would get from MIT GCM, because certainly you have it. And also a second, like more technical, practical question was, in which frame are actually the outputs? Is it a 2D velocity field or a radial velocity field? And if it's a 2D, in which direction? Is it the northeast velocity vector or along a cross swath?
Right. So first question, I think that's probably a good idea, releasing an actual data set so people can just play with the data. I have no problem doing that. So maybe we can start putting that together. The second question, so this simplified simulator is just in east-west velocities with errors on the east-west, or geographically oriented velocities.
And the same error and uncorrelated between northward and eastward velocity. So it's a random noise different for each component. Okay.
That's right. However, we have another simulator that does what you're describing, that does radial velocities, that does all of the real errors on radial velocity and then propagates through to the east-west, north-south velocities. I'm not planning to release that one because it has a lot of radar information in it. But if it's something that's particularly useful to someone, those outputs, I might be able to provide some of the outputs.
Thanks a lot. Yeah.
Yeah, of course.
Alex, I have a couple of questions about this slide then, if no one else is asking.
Sure.
It just getting back to the question of how you computed the errors and the question of also what the time scale was for the simulation over which you did this analysis. Did you do it for a full year, sort of averaging by 4 days and that sort of thing? So that's one question. And the other one is for the measurement noise. Did you use a wind speed dependent measurement noise or the mean at 6 meters per second? Is that what you said? So that maybe is one of the difference with the results that Dudley's paper showed, that
Right.
possibly that mean baseline noise that was actually used is a bit smaller than in that paper. Is that correct?
It's slightly smaller than that paper. That's right. And it's not wind speed dependent here. The original paper, that Wineteer 2020 paper, I have the wind speed dependence in there with the full, more complex simulator. This was just done all with the more simplified error model in the simplified simulator. Your first question was about whether I did the 4-day averaging for a year or a long time period. I did not. I just did it for a 4-day repeat cycle, just one single repeat cycle to look at the errors. Of course, eventually I should do it for a longer time period. It's just haven't gotten around to it.
Oh, okay, thanks. So some of those global patterns might move around a bit then, depending on season, because of the wind speed dependent errors. Is that right?
Well, they might move around just to changing currents and the SNR that you end up getting, but the wind speed dependence isn't actually in those plots, so it won't be the wind that does it. But in reality, there will be some level of dependence based on the changing wind speed.
Okay, great. Thank you.
Mm-hmm.
Any other questions? I can see that there have been some useful comments in the chat from Elizabeth Remy about assimilation and from Ad about rain and what it might do. And I probably have a stack of questions, but maybe in the interest of letting people move on, we should wrap up. This has been really great, really interesting and a good discussion. So thanks, Alex, and thanks everyone for participating.
Yeah, of course. Thanks for having me.
Thanks a lot. Really interesting.
I'm going to stop recording.